activity two, part two is for you to complete in your own time, essentially, based on what we do now, and it will give you some idea of how you can use the outputs of PetThermoTools to interact with other, um, yeah, other Python packages. And I do appreciate that the one face I can see is Brad's here, because this activity is shamelessly stolen from Brad, I believe, or Brad's idea. So thank you, Brad, for the idea for this. So yeah, what we're going to do is basically going to talk through how you run fractional crystallization calculations, how you can visualize some of the results, and rather than just running arbitrary calculations, this is something I actually did with my petrology class a couple of years ago, the first time, is we're going to ask the question of how do the conditions of crystallization, so specifically thinking about pressure, oxygen fugacity, water, don't actually investigate CO2 in this, but you could adjust the code to investigate CO2 as well. Could these influence whether or not you end up following a calc-alkaline or foliatic differentiation trend, is essentially the idea of this activity. And when I did this in my class, I used the Aleutians as an example for this, just because as in a very general term, as you go from that kind of northeast corner up here, where you have more of kind of like continental arc style of volcanism, you typically see quite a few systems that have a calc-alkaline differentiation trend. Augustine is going to be our example for a calc-alkaline system in this case. And as you move further towards the southwest, you typically go more towards foliatic differentiation trend.
You're not sharing your screen.
Am I not?
Oh no, you are. Hold on, you are for me. I read that out. Someone says you're not sharing your
Mm.
screen, but you are sharing your screen.
Okay, sorry.
No, I can see your screen. Can
M-
everyone else see their screen? My
Make sure
screen?
you got Zoom maximized and Zoom isn't just in a little pocket.
I see the screen.
Okay. I just okay. No worries. Okay, yeah. So as you kind of move towards the southwest, you typically get these systems that are more foliatic in their kind of differentiation trends, especially you kind of move towards something that's more akin to like island arc volcanism out here rather than continental arc volcanism here. I don't know if we have anyone from AVO here who could probably tell me if I'm getting this completely wrong, but I'll go with it until someone speaks up. And so the idea is basically, okay, if we're having primitive magmas generated in this system, could differences in their kind of initial properties, such as their oxygen fugacity or maybe the pressure which they're stored, could these kind of factors or their initial water content, could this influence whether or not something ends up going down a calc-alkaline differentiation trend, so initial depletion in iron or no enrichment in iron, rapid enrichment in silica, or a foliatic differentiation trend where you get this initial iron enrichment during the crystallization. Okay. So that's the kind of idea of this. So just to start with, we're going to import everything that we've done before. So import NumPy, import pandas, matplotlib, and critically PetThermoTools. So if everyone just run that first cell, and hopefully you should get something like this. I have noticed on a couple of people's, it's printing the please append using syspath when actually that isn't necessary. So if you've been using the sys.path append and it's working, keep using that. But actually, there seems to be a little bug in the messages being printed. It's not working perfectly. I will try and fix that moving forward into the future. Because I'm on a Mac, I am going to run this twice. I'm not actually going to do it just yet because I might show you guys what it looks like if I don't. Actually, no, because I have to go back and run anything. So I'm going to run this twice. And if you're wondering what the platform system equals Darwin is, this is basically identifying the Mac operating systems. So if you're Windows and you run this, it's going to do nothing. So you can run it, don't have to worry about it. If you're on Mac, run it twice. So we are going to come down into here. We're going to load in this Aleutians XLSX file. And you will notice that once again, we've identified the same three volcanoes. You can notice the kind of theme in how we're kind of separating things here. So this volcano.unique, I'm basically asking in the Aleutians data frame that I'm creating, I'm just asking by doing that by saying volcano.unique. I'm just asking in this column volcano, what are the different unique values that I have? And so you can see in here, I have three separate unique values. So what we're going to do to start with is we're going to define a starting composition. Okay, there are various ways to do this. We could load it directly from the Excel spreadsheet. We could load in one of those rows in the Excel spreadsheet as our starting composition, or we can type it out like this in a dictionary structure. I'm doing this here so you can kind of visualize kind of what it looks like. So here I'm specifying a silica, titanium, aluminum, iron, etc., etc. And then in this dictionary, it's key item. All right, so you got your silica at 50.04. Notably, the way this is treated in alpha melts is you're actually providing the system in grams of material. So the way it usually works in alpha melts with Python, alpha melts, you're providing a number of grams of material. I made a decision early on to really treat this more as a kind of weight percent. And so things are normalized to 100 during that first step of the calculation. So in terms of the outputs, it will output a volume, it will output a mass of the system and things like that. All of those outputs are kind of assuming your system starting at 100 grams. And it basically means that these inputs are more of a weight percent rather than a gram inputs in that sense. Okay. So this is our composition. Okay, so this is a composition actually taken from a melt inclusion, I believe from Okmok in this case. And we're just going to run this calculation here. This is our isobaric crystallization. I'm British, so I spelled it with an S, not a Z. I now have been living in America for too long, so I now say C instead of Z. I'm quite annoyed about that. But isobaric crystallization. So single pressure crystallization, we can once again go through our arguments. We are going to use melts 1.2.0. We don't have any CO2 in here, but there will still be a slight difference between 1.2.0 and 1.0.2 because the water solubility model is still different. So the activity of water is different. One thing you could do is test this with 1.0.2 and see how different the results are. If you have time later, something to try. Our bulk composition is just going to be this single variable. Okay, so we're just loading one bulk, whereas everything we did with Penny, the SAT-P, and the equilibrate, we were loading multiple bulk compositions by providing a data frame. Here we're providing a dictionary, so it's just one composition. Tell the system to find the liquidus. We can either set a starting temperature, so there'll be an argument T start C, or we can just tell it to find the liquidus, and that's the first thing it will do. Set a single pressure, estimate the water content, what temperature do we want to end the calculation at, and the temperature step. So in this case, it will go down to 900 degrees. We'll set our oxygen fugacity and an offset, in this case, just keeping it at the FMQ buffer for now. And we're going to do fractional crystallization because I'm setting true here and here. Because we're running this on Zoom and Zoom seems to take an inordinate amount of CPU usage, I'm going to increase that timeout to 180. That's going to give everyone's computers 3 minutes to run this calculation. It should run far quicker than that. Okay, so I'm going to run that calculation there. And this is going to, so it's going to start, the first thing it's going to do is find the liquidus, and then it's going to drop in 2 degrees Celsius increments. So it took 5 seconds overall until it hits 900 degrees Celsius, or the system hits a failure point. And if it does, it will return the calculation up until that point. Okay.
And Matt, do you want to just quickly explain what would happen if you set frac solid equals false and frac fluid equals false?
So if I do so one way to look at that difference would actually be to look at, one of the outputs data frames in the dictionary is mass. Okay, so this is the mass of the system at every step. And you can see in here that there's the mass of the liquid, the mass of pyroxene plagioclase. And if you were to sum just these 5 columns here, you can see that in this 116th row, it would sum to what, approximately 29 grams. Whereas in the first row, it's summing to approximately 100 grams. It's not quite 100 grams because we're using an FO2 buffer, we adjust the ion redox after the normalization is done. But over here, I then calculated the cumulative amount of pyroxene, cumulative amount of plagioclase as well. If I set these to false.
And this is what you would all call your typical fractional crystallization. This frac solids equals true.
Yes, in this case, the frac solid and the liquid are going to be kept in the system during crystallization. We no longer have that cumulative sum column. And in this case, you can see that the sum is approximately going to equal 100 on every row. It's not actually going to perfectly equal 100, but it will approximately equal 100 on every row. The reason why it's not perfectly equaling 100 is because we've set an FO2 buffer. It's an open system. We're allowing oxygen to exchange into and out of the system in order to maintain that buffer position. If I had instead set an ion redox state, Fe3, FET underscore init would be the argument there. So instead of this, I could set an initial ion redox like that. And then I would have to get rid of these two lines. The mass of the system should stay far more constant. There'll be slight variations just in order to allow. There you go, perfect. I was expecting it not to be perfect. 100 exactly, because we've set an ion redox state. So by doing the oxygen fugacity buffer, in order to achieve that buffer, it's an open system. So your mass might change very slightly during that. Go on, Penny.
Okay, couple of clarifying questions we've got that are great questions. So Juliet
Yes.
has said you didn't include Fe2O3. Paul said we have to do that. Okay, yeah. So basically what PetThermoTools does is it allows you to specify it as FeOT liquid. That's because that's what you're getting off the vast majority of instruments. How we then specify the amount of Fe3 plus is you either specify that redox buffer. So what Matt said at the start when he was doing FMQ to 0, what that's going to do is that's going to partition your FeO total between Fe2 and Fe3. Your other option is that you can specify an Fe3 Fe total ratio in the calculation. And yeah, Matt, what did you just do?
Yeah, so that we do a couple of, so Paul absolutely correctly said you need to make sure you have minor components. For some of those minor components, we do have inbuilt checks in PetThermoTools to make sure you're doing it. And so one of those is the ferric ion. And so what I did here is I actually just deleted the FO2 lines and I deleted the ion 3 line. And so basically what the code is going to do, it's going to check either you need to have in your initial bulk composition something about ion redox, so something up there in the bulk composition you're going to provide it, or you need to provide an ion redox information here, or you need to provide an oxygen fugacity buffer information. If none of those three things are provided, it's going to actually stop your run. It's not going to give you a run. It's going to say it's going to fail to produce any results. We've got no ferric ion. Please give us something. And so even if you put in 0.001 Fe3 FET, it will then run. Similar thing if you do no water, it will once again say we need a little bit of water. It becomes really unstable for crystallization calculations, especially with absolutely zero water. So even if you're just putting in really nominally anhydrous like concentrations, 0.002 or something, it will help. And so yeah, just a couple of things that we have built in to kind of make sure that those kind of things Paul talked about, those minor components are followed when people are running these calculations. And so yeah, what I was talking.
Sorry, Matt. The second clarifying question was people just want to clarify exactly what you would put for fractional versus equilibrium crystallization, as they're the terms that everyone typically thinks.
Yes, so fractional versus equilibrium, you're literally just changing those from true to false. As default, they're on false. So if you don't specify anything, if you didn't include these as keyword arguments, that's equilibrium crystallization. If you include these and set them to true, that's fractional crystallization. And it does also obviously give you the option to only fractionate fluids and not fractionate solids. So you can have like a intermediate in some ways between those. I have been considering, and if people are interested in this, I can potentially put some time into doing it, building in not just an on-off statement, but allowing a percentage. So a fractional crystallization or continuous crystallization where like 10% of your melt of your solid phase remains in the system or something like that.
Yeah, that's actually already implemented underneath. We just need to
Incorporate. That's it.
yeah.
Yeah,
It's
so
all in there.
if
It's
people are
just
interested in, we can prioritize getting that working.
Yeah, that's the kind of thing that I was talking about when I was saying that there's quite a lot of things that are almost implemented but not hooked up because we need to have some examples to run.
Yes, absolutely. So yeah, if people give us the information like, oh yeah, that would be really useful for me, it gives us the motivation to go through and like get this working because we have 1,000,001 things to do. And so if we hear something, if you hear me say something as this is something we're working on, let us know that you're interested in that and we'll prioritize it basically. Because we're slowly working our way through our list. But yeah, so
Sorry Sorry, just quickly, could you show people how to access the help for this function? Juliet is asking how you would know what the syntax for FE3, FE total is.
Yes. So this is easy if you're on Windows. If you're on Mac, it is not easy. The reason why it's not easy on Mac is because of that statement there. So what I'm going to do is I'm actually going to restart my kernel and show you how it would work if you're on Mac. But basically, for all these functions, once you've imported PetThermoTools and before you've turned off the output, so if you're on Mac, you can write a help statement, type in the name of the function, and it should print out the documentation like this. So it will tell you what the different options are. So we have 6 different thermodynamic models to choose from. In this case, we have our bulk, which can be either a dictionary, so a single value, or a pandas data frame. So you could load in an entire Excel spreadsheet and run crystallization calculations with every single value in an Excel spreadsheet. Our frac solid, frac false, sorry, frac solid, frac fluid with default false, temperature information, pressure information, redox state, sorry, ion redox state, oxygen fugacity material. This useful one down here, label, I'll talk about a bit more later. And then there's a few other parameters that I'm not going to talk much about today, but you can also stop calculations at a certain crystallinity. So I've been doing this in some work on some high silica rhyolite systems, where I actually stop the system once it gets to like 60% crystallinity, rather than letting it go to a lower temperature, because you get too close to the granitic minimum, you increase your chances you're going to hit a calculation failure and melt. So I'm doing it based on a kind of like rheological locking point in the system. Fluid stat, if that's true, and you put in 40 weight% water for some reason, it will actually just like remove that excess water from the system. So you just start with a magma, no excess fluid. Our timeout function, and then these suppress phases are there if you were getting something really weird in your calculation. Say you're getting whitlockite, which is a mineral melt sometimes predicts, and you don't want whitlockite, you can add a suppress equals whitlockite, and it will remove that from the potential model outputs, essentially.
And Matt, and a way that Mac users could easily deal with this is just open up a new notebook and you can just load in PetThermoTools into that notebook and use that as your help access for now. So
Yeah,
you could just have a second
that's a good
notebook
idea.
and then you can just call help for all the functions until they work out how to suppress the outputs
Yeah.
properly.
Yes. Okay, I'm just going to quickly run through this again.
Yeah, so
And
people are just asking about this help statement. So Matt, just to make this easier, could you make a new notebook and just show people what they'd need to pull in if they're on Mac to and then Matt can paste this in the Discord. You'll also need to, if you haven't got the installation thing, you'll need to do the sys append thing.
you won't for help.
You won't for help? Okay.
No, because
Oh,
you're
you're
not
right.
actually
It's just
accessing.
pulling the yeah.
So
So
like
all you need is this.
you just want that and then help whatever function you're looking at. So everything we've looked at so far should have relatively extensive documentation in it. That should give you the parameters that you expect and also what the output should look like. The output should all look pretty similar for most things, but all the information should be in there on what the parameter options are. That makes sense.
You'll notice that something Matt's computer is doing is it's auto filling these things in. That's another advantage of VS Code. Is it kind of knows what the functions are called. So it's like you don't have to actually finish typing things. Equally, when you go to like find a column name, it actually knows what the column names are. So it will often auto-complete. So that's just so you can see here, for example, it's like starting to type out the options.
On VS Code, and I think some Jupyter Lab does this as well. If you hover over a function, it will give you the base variables that you can call. I don't know if all versions of Jupyter Lab do that, but I believe some do. VS Code does as well. So this doesn't give you all the documentation, but you can see what the parameters are and what I have as the default settings for some of these parameters as well. All right, so I'm just going to quickly go back to here. So we ran this isobaric crystal calculation. And just like Penny was showing with the equilibrate calculation, the output is exactly the same. The idea is for most of our calculations in PetThermoTools, we're trying to keep things as similar as possible to make it easy to go from one function to another. And so the same thing here. Our output, if we were to do type isobaric crystal, is dictionary. Within that dictionary, we have various different things. So we have our conditions, we have our liquid properties, our Kleiner pyroxene. So we're separating out composition and thermodynamic properties in here. And we have that for all the phases present within the system. Okay. There are various other useful things in here. So Penny mentioned like the phase list earlier. We also separate out the masses into a separate data frame. That's what I use to kind of look at that cumulative sum and the difference between equilibrium and fractional crystallization. Volume and density are ones that we've chosen to kind of separate out in this case. One thing that can be quite useful, and I will talk about it in a little bit, is when you run multiple calculations, you also will get an input data frame. I don't believe this does it for individual. It doesn't do it for individual, but when we do multiple ones, you will see there's an input data frame. So all of these, we can kind of call that initial data frame from the larger dictionary to get those parameters. And so if we wanted to look, for example, specifically at the water content of our liquid as crystallization proceeds, you can see it starting around 2 and increasing up to around 6.7 during fractional crystallization. We could also then compare that to the mass. So if we just show the liquid property data frame in here, see it all still has the underscore phase associated with it. So we could then, if we want to look at the mass, you can see that we're going from almost 100% melt fraction. There was a little bit of Kleiner pyroxene at that liquidus point, down to around 27% melt fraction at the end of this crystallization model. Okay, so I encourage you guys to kind of play around with these outputs, learn how the output structures work. I hope they're logical. I designed them so they're logical to me. That has no guarantee it's logical to anyone else. I do realize that, but hopefully it's relatively logical as to how you kind of get a certain parameter you might want within there. Okay. The other thing we can do with this output though is we can start to plot up some of the results. So here we have this ptt.harker. So why don't sorry, I need to hide the meeting controls. I can't see this chat anymore, I'm afraid. So we can actually go help ptt.harker. So this is for plotting basically compositional oxide versus oxide plots. Okay. So it's telling us by default, we're going to have magnesium on the X. And by default, it's going to basically put the whole list of other oxides it's aware of as y-axes. And by default, it's going to plot the liquid phase. All of these are things you can change. You could put silica on the X. You could only include a couple of things on the Y. You could plot your composition of your Kleiner pyroxenes if you wanted to. The other thing we can do in here, though, is we can actually include data. So this is external data, not from the calculation itself, that we might want to plot up against the calculation. And you can either load this as a data frame, or you can do what I've done here and load a dictionary. So here I have each volcano, and then from the data frame, I'm just identifying just the rows that have that volcano. So if we kind of examine what's happening here in more detail, is I'm saying locate the rows where the volcano in the column of volcano in this data frame is equal to Shishaldin. I think I spelled that right. And then it would just return just those rows where this volcano column has that string argument in it, okay? And so this is a way that in plotting this material up, and I could change this to Augustine as well. In plotting this material up, I can separate what was initially one data frame into 3 separate systems, okay? One for each volcano. And then if I run this cell, and actually, yeah, I think it was Lynn earlier, the semicolon advice that will get rid of those prints. You can now see that we have our fractional crystallization model in the black, and you can see the green colors here are Okmok, the orange are Augustine, and the blue is Shistaldin. This starting composition is actually from an Okmok melt inclusion. It's not from this data set that we loaded in itself. But that's why it's going quite close to these green samples on most of the curves is because actually it's an Okmok melt inclusion with anomalously low potassium contents. Actually, I just spotted over here. But anyway, so this is kind of comparing that fractional crystallization model to the data itself. So I give everyone a chance. Can you give us a thumbs up in Zoom if you've managed to produce this graph? Thumbs down if you're having issues. I'll keep an eye on the Discord chat to see if anything's happening.
Well, Matt, do you want to get them to change the x-axis parameter to silica and then they can post their results?
Yeah, yeah, that's a good idea. Why don't you, so if we kind of move that down, why don't we change, so x-axis equals, and then change the x-axis to something else? You could also try specifying a string of y-axis parameters, so not a string, sorry, a list. So within here, you might want to say TiO2, MgO, and y-axis, let's roguely put it to FeOT, or something like this, and see if you can recreate some different plot. So that's my one. Have a go changing the x and y, and see if you can create a different plot of, yeah, maybe silicon on the x-axis makes more sense for this system. I'm typically a basaltic guy, so I work with magnesium on the x-axis in most cases. But have a go changing up those parameters in here.
And again, if you ever want to know, like, how do I change the parameters? So we got a great question in the chat, which was, how do I edit the symbols, colors? Have a look at the help function for PTT Harker and have a look at what it says and try and suss out how to change the color. Maybe make the model color red. Have a quick play, post your results, and then Matt can just quickly go through how to do that as well.
Yeah, so there is one of the examples on Read the Docs, one of our fractional crystallization examples, has an example of the Harker plot, which specifies, I'm just letting it choose its own symbols here. One of the examples we have online does specify certain symbols and certain colors for each symbol.
Brad has asked about the order. Looking at the way you set up the function, the order doesn't matter for this, does it? They can put the arguments in any order.
Yeah, so typically I always use what are known as keyword arguments. And this means that you have to say like results equals to rather than just providing a variable within the parentheses. And it means that the order doesn't matter. So I could put results at the end. It'll work absolutely fine as well. Yeah, so your plotting is working, your melts is not. So the melts calculation, Dawn, doesn't seem to have run, but the Harker function still works for plotting your compositional data. I have to
They
work
might
out
not
why.
loaded or installed melts if they're doing it the syspath append
Yeah, so
way.
make sure the sys.path append. So the sys.path append, you got to make sure that's pointing to the folder that contains the melts dynamic.py file. The best way to test is to run that ptt.test underscore alpha melts. If it doesn't have the um the the correct file on the path, it will return an error, hopefully within a couple of seconds.
Matt, can you just type that command in the chat for
Yeah.
people?
And obviously you need to do your sys.path append in addition to that.
I just pasted in the code for that.
Oh, nice.
Up above.
Yeah, so we've got a nice silica against titanium plot in here from MAD.
Is there an easy way to adjust the spacing, Matt? I'm guessing that's not a keyword argument you've set up.
No.
I would say in general, folks, with these plots, the logic was these plots are great for visualizing your data. To make it fully customizable, we'd turn it into like a monster function. So generally we're assuming like you'll use this, you'll run your models, and then when you actually go to make your publication figures, you'll use your matplotlib because you will want to make your plots a very specific way. This function is more for like easy visualization when you're running the models.
Mhm. Yeah, I mean, I can show you briefly what the underlying code looks like, but there's only so much that I can control in here. And so in terms of actually setting up the figure axes is basically just a width per number of columns per number of rows, which are defined by how many y-axis variables you specify, essentially. So no, I don't have a way to control the spacing directly in the function that I have built for this. If that makes sense.
Matt, could you quickly show just quickly how to change the colors, as that's the color of the symbols? That's really the thing people are most likely to want to do.
Yeah, so decolor is the keyword argument for the color of the symbols. And I'm going to not use green because people might be colorblind. But so basically, you just have to make sure when you specify decolor, you provide a list of colors. So here, just an RBG, you could provide a true RGB code in each instead. But you just got to make sure that the length of this list, so I've got 3 parameters in here, matches the length of the number of different things that you're loading in terms of data in this case. Okay, so you've got 3 different data sets, 3 different colors, and D underscore marker, so data marker, data color is the same thing. So we can have circle, square, diamond in that sense. And then, well, we've got Shishaldin as a red circle, Augustine as a blue square, Okmok as a yellow diamond in that sense. I don't believe I've coded in the size parameter yet, so you can't specify size for different symbols, I'm afraid, in this. But as Penny said, this is a useful initial pass. You might want, if you want to produce a publication worthy figure, you might want to eventually, yeah, design your own, yeah, plotting tools or plotting functions in that case. But hopefully this allows people to visualize what's going on relatively nicely. All right. Oh, so that test works well, but you still get the same plot. That is strange. Okay, I'm gonna, yeah, if necessary, Penny can hop in a breakout room and see what's going on, because if that indicates the installation's worked okay, so it's odd that it hasn't run through. But it does look like a lot of people are getting good plots. If there's anyone else that's still struggling, send me a thumbs down. Otherwise, if people are happy to move on, send a thumbs up. So Jay-Z, your question there, this was a very good point. Basically, what Penny suggested doing is you open a new notebook. So you can see here, I haven't even saved this anything. It's just a brand new notebook. I imported PetThermoTools and then help and then ptt.function name, and that will allow you to view this. So just having a second notebook is unfortunately the best way to do this. It's not ideal. Okay. I've now lost the ability to get back to my proper notebook. 1 second, everyone. Okay, is everyone mostly happy to move on? Has anyone else got any major issues that they can't seem to solve at this point? Was everyone able to run this okay? How long did that take, those that fractional crystallization calculation? Just to give me an idea of how long I need to give everyone for their future calculations. Was it rough? Were people roughly getting them done in around a minute or less? Seven seconds. Okay. Yeah, so hopefully what we were doing before, trying to set up 64 different calculations of saturation pressure is always going to be slower than this. Or we have one calculation that's just going to go down in this picture. That's a far quicker way of doing it. So if we're in like the kind of 7 to a few seconds to a minute, that's kind of what I'm expecting for this. And it will be slower while Zoom's running. If you do it by yourself, it'll be much quicker over there. Okay, the next function we have down here is once again an inbuilt function phase plot in PTT. So once again, we can come over to our help phase plot, and you can see here that basically this is going to create a kind of stacked area plot with the phases predicted by the thermodynamic model. So we need a data frame that has a mass function and an all function, and it's going to return a figure with the kind of information in terms of phase proportions in that case. So everyone give a chance running that. You should see something that looks something like this. Okay, so you can see initially our system is almost entirely liquid. It's going to run down and we're going to increase the proportions of other phases. I need to change this y-axis value, I've realized, because I call it mass fraction. This is mass fraction relative to the starting point of the system. Because we're running at a buffered oxygen fugacity and it's an open system, the mass of the system is actually changing slightly, which is why it's slightly higher at the end than it is at the start. So if people are wondering why there's a little white strip at the top here, that's why. Have a go running that. Have a go. You can change your, if you think magma is more appropriate for what we're talking about, you can use the magma color map in there as well. If you didn't want to do it with temperature, say you wanted to compare some things, you could use the magnesium content. The underscore liquid is because in the output data frame, we indicate the phase by liquid over here. But you could run this to look at the phase proportions at any liquid composition as you undergo fractional crystallization. Okay. You can do the exact same function, but specify lines equals true. And that's going to plot a very similar thing, but each line is going to independently show the mass fraction of that phase. So you can see our liquid dropping down throughout the crystallization interval. Our clinopyroxene and plagioclase are the two most abundant phases, with clinopyroxene actually forming the initial early phase, dominant crystallization during the early crystallization. And then these other minor phases, including some small amounts of olivine, spinel, and a secondary, likely a low calcium clinopyroxene as well over here. Okay. All right. If anyone's... Oh, great question. So Brad's asked, the added water can cause it to be above 100% if you start with nominally anhydrous composition. Yes. This is an important point that Penny and I had many arguments about how best to deal with this. Essentially, the composition that you provide will be normalized to a hydrous total of 100 prior to calculation. So if you run not oxygen fugacity, not buffer fugacity buffer, it should be 100 grams when you start. The key kind of like distinction or differences in here really come from the fact that when you provide water in the system, so there's actually two options. I provide water here as H2O init. I could have provided water in the bulk variable as well. If water is included in the bulk variable like this, every parameter in this bulk variable will undergo the same scaling in order to match it to 100 grams. If, however, your water is provided with this init variable here, the water will start at 2 weight percent water, and your bulk composition will be normalized to 98 grams anhydrous. Okay, hopefully that makes sense. So basically, this was something that Penny thought would be requested, is that if you specify the initial water of 2 weight percent, people will likely want the water content to start at 2 weight percent. So we start the water content at 2 and scale everything else to 98 in this case in order to keep that water content at 2 weight percent. Okay. Hopefully that makes sense. Awesome. Okay. I'm going to assume, I've seen lots of people posting their results, that most people have been able to run those calculations. I know Penny is working, trying to fix a couple of ongoing bugs. So what we're going to do now is we're going to come down to this part 2. And what we're going to do in here is we're going to run this calculation once again. So the same thing, I probably, for you guys that was taking a bit longer, once again, increase the timeout to maybe 180 again. And we're going to run this calculation. There's a couple of differences. It's almost identical. The only difference is we're now providing a list of initial water contents, and we've said label H2O init. Okay, so I'm just going to run that and then talk about what these all mean.
Can I ask you to help to hop on to Dawn's, because I can't debug her installation, and I'll take over for this for a minute.
If I hop on, I'll lose the recording. Do you want to swap
We could swap
rooms?
laptops. Yeah, hold on. We'll
Swap
do
rooms.
a switcheroo. Hold on. I don't know how to use a Mac though. Right. Hi everyone. I have now become Matt. Hopefully you can all see me. Okay, so hopefully you have all run this. This is where I really don't know how to use someone else's keyboard. So this is a little bit different in how it's outputted. So if we look at the keys for this, what you'll see now is instead of those keys being things like all liquid one compositions, you now have the keys are actually these different conditions that you set up. So you basically got another layer of your dictionary. This is where you have to stop imagining your dictionary as one Excel spreadsheet with different rows. This would be like different Excel spreadsheets within a folder of your computer. So we basically got a dictionary which has a key for H2O 0.5 weight percent. So that would be your calculation with half a weight percent water. Another one with 2 weight percent, another one with 4, another one with 6 weight percent. So if you grab this key and we put it on this with square parentheses like that, what you'll see is you now have the same dictionary that you had before, now that you've entered into this model where you have half weight percent water. So again, we can look at the keys for that, and we can see we now have the keys that we had for the last example. So what we can do is we could look at the liquid composition, for example, here. So that would be the liquid composition for half a weight percent water. If we wanted to look at the liquid composition for 2 weight percent water, we would simply change, this must not be the actual key. 1 second, let's just look at it. Sorry, this is not my laptop, so I'm not used to Macs. Let's just paste this here and see what the keys are. Sorry. Oh no, it's not going well at all. And now I can't. All his faces in the way. Right, 1 sec. This is very embarrassing using someone else's laptop. Dot keys. Let's just see what the key is called. Okay, so it's 2.0 weight percent water. There we go. That's an easy trap for the unwary. Okay, so there we go. That would be the water content for 2.0. Okay, so now what you're going to do is you are going to take the Harker function that we used before, and instead of feeding it the dictionary for the one calculation, you're going to try feeding it this dictionary, and we shall see what happens. So have a go at copying this Harker code from up above, and then we can put it in here. And then again, once you've done this, you can all post your results into the Discord. The results is now not called isobaric crystallization, it's called isobaric crystal H2O. So hopefully everyone has got something like that. Obviously Matt isn't showing all of the oxides because he's added this y-axis argument, so we can delete that away. And we can see that these are all of the trends. And now we can see that we've labeled these, so we know what different water contents. Now, Matt, iron is a horrible x-axis to have put down, so let's change this to a more reasonable x-axis. So folks could just type in the Discord, what are some things you've noticed now we've changed the water content with the trends that we're taking in elemental space? And what minerals might you hypothesize have caused those changes? So you can put this in the post your answers. What are the big differences between these models? Yeah, Brad has correctly said plagioclase is different. So when we think about plagioclase, we can think about that aluminum content, and when that's really starting to tank when you're taking out plagioclase. There's 2 other oxides which are really distinctly different between these models. What oxides would we say that those are? So a big one for me that sticks out is this titanium content. So you can see that low water content model at half a weight percent shows that really drastic titanium enrichment up to about 1.7 weight percent and then drives down. Whereas you can see in contrast, this really wet model at 6 weight percent never shows any titanium enrichment. It's dropping the whole way through the model. That tells you that you are fractionating a titanium rich phase pretty much all the way through. Similarly with iron, you can see that dry model shows that prominent iron enrichment and then it drops down again, whereas there's very little iron enrichment in that very wet model and then it drops down again. So you can also plot phase plots for these, or we can plot these on our, famous calc-alkaline thermolytic diagram. So that's what we're just going to do here. So I'll just talk you through exactly what this code is doing. So we're just specifying an x-axis and a y-axis. And we're basically looping through these keys. So those keys, if you remember, were the key for 0.5 weight percent, 2 weight percent, 4 weight percent, and 6 weight percent water. Within that, we are then defining this variable FeO over MgO, which is the key. So that's the 0.5 weight percent water or whatever, and then the FeOT liquid divided by the MgO liquid. And then we're making a plot which basically shows the iron versus the silica content. And you can see so far, all 4 of these models are technically thermolytic, but we can see that drier composition, that 0.5 weight percent, shows a much more thermolytic path than the other ones. The other ones are pretty close to this calc-alkaline divide. Matt, are you done? Do you want to swap that?
Yes.
Okay, now you get Matt back again. I just explained that. I think you have.
Awesome. So I have absolutely no idea what everything's got to, so we'll go through it all again. No. So one thing I did just note is a couple of people were saying they got like plots with no melts models. Make sure to change the timeout. Putting it as 30 seconds was too short. That was my mistake. Make sure the timeout's like 180 seconds or so, just in case. If you happen to be on a computer that's struggling, running Zoom and Python, that might be the cause of not getting any calculation back. Yeah, so hopefully Penny's shown you that these are all technically fodiites, and also one of the really nice things you can see on this plot here actually is as you increase your water content, you really suppress that iron enrichment. And I think I heard someone mention that this is likely due to the onset of plagioclase crystallization in that case. Okay. So now what I'm going to do, hopefully everyone, I can see Brad put plagioclase up there, perfect. What I can going to get you guys to do is I want you to do the same thing. Okay, so here I just have a blank isobaric crystallization call. What I want you to do here is I want you to fill out this call with all the keyword arguments. So you specify the model. Do you want fractional, frac solids, frac fluids, find liquidus, all these keyword arguments that specify an isobaric crystallization run. But I want you to keep water constant. So choose a water value that you think is appropriate for Aleutian volcanoes. And instead of varying the water content, let's vary the oxygen fugacity. So you're going to need to specify a list of oxygen fugacity offsets. We'll specify the buffer as FMQ, specify a range of offsets from FMQ, and also change the label. Change the label from water to oxygen fugacity. What the input parameters are called, that's what the label should be.
Quiet. It's not just me that thinks this. You might need to either unplug your microphone and just use your speaker. Something's gone wrong.
Oh, okay. Sorry.
I couldn't hear you, but I thought it was me that's just broken my computer.
I don't have a way to plug that in right now, but I'll go grab it in a sec. Okay, I'm just going to speak up and then I'll go sort out my microphone in a bit, but hopefully everyone can hear me well enough in order to follow this. So basically, what I want you guys to do is I want you to complete this code. Okay. So we have this isobaric crystallization code here. I want you to complete it, but rather than varying the system water content like we did above, in this case, I want you to vary the oxygen fugacity. So we're going to do this by varying the FO2 buffer keyword argument, providing a list of values to that argument. And we're also going to change the label. So rather than labeling by water, we want to label by oxygen fugacity. Okay. I'm going to quickly run and go grab a better microphone, and I'll be back in 2 minutes. No, it's all right. No, it's good. I just need to grab something from the garage. Brad, if it's only showing two calculations, one option is it might be that it timed out before it returned the final two calculations. So try increasing the timeout a little bit, um, and then see if that works.
Great, thank you.
Am I clear on audio now? Just so. Can... Hopefully you guys can all hear me okay?
Much better.
Cool. Okay, yeah, so for this, like I'm gonna let people keep
No one's posted their no one's posted anything in the post your results.
yeah.
So if people have got that to finish, if you want to screenshot that it
Mhm.
worked and produce something just so we know where people are at. Otherwise, Matt
Yeah.
can just quickly now talk through what you should be doing.
Yeah, so as I say, I think for the timeouts here, it was my fault. I had set them for what my Mac does. If your calculations are taking longer, I would definitely increase the timeouts to like 3 or 4 minutes. The single calculation as a kind of scale on mine took around 5 seconds. So I would definitely increase the timeout just to make sure you give everything the chance to run in this case. So what I'm actually going to do just to kind of get an initial start to this is I'm just going to copy all the input arguments from the H2O run and copy them down into here. I'm then going to change a few, but the majority of things can stay the same, right? So the majority of things can stay the same. We're using the same model. We're using the same starting composition. We want to find the liquidus. We're going to keep it for now at the same pressure. We're not going to use multiple water contents. We are going to keep it at FMQ, but we're going to specify multiple offsets from that buffer, and our label needs to change. So essentially in this, what we're asking you guys to try and do is input three new values. So something for the water, something for the FO2 offset, and something for the label in this case. And if you do the label correctly, when you make the plot, it should, as we've seen a couple of people already starting to plot this in, which is excellent. We should be able to see when you make the plot, it will label those lines according to the oxygen fugacity that you see. So yeah, some people are starting to get these plotted up, which is excellent. And someone that's plotted in Discord already, post in Discord or on chat here, what do you think is the major difference for oxygen fugacity versus water content? What has a bigger influence on whether it follows calc-alkaline or phodiatic crystallization trajectories? I see people doing it with the Harker plot as well, which is excellent. So rows, because your ones came out as run 0, run 1, run 2, run 3, run 4. Those are like the default numbering. And it basically means that the label argument wasn't correct. So I think the label here can either be FO2 or it can be FO2 underscore buffer. I believe either will work in this case.
You've written in your docs, Matt, that it's FO2 offset.
Oh, sorry, FO2 offset. Sorry, yes.
So I've just pasted a screenshot in the Discord help channel that shows what the allowed labels are. And they are H2O init, P bar, FO2 offset, and FE3 FET underscore init. So Alex, do you want to try running with the label slightly differently and seeing if you get more than one key?
Your Alex, so one of the things is because your water is provided as a list as well, it might be recognizing that basically the code is checking the length of different options. So it checks the length of the input composition, it checks the length of the water, checks the length of the FO2 offset, and it's kind of going down a hierarchy on how to define which has the length to use for the calculation. I think it might be seeing that H2O init is length 1 and using that as your length.
And Matt, I'm going to add an issue on GitHub. So if they supply more than one list, you tell them that's not allowed.
Yeah,
because
that's a good
idea. Shouldn't be a good spot, Alex.
Yeah, this is why it's useful to know these things so we can work out what can go wrong. So yeah, basically, if you're providing more than one list, in a variable, the list should match length. Otherwise, you won't get the number of calculations you expect. So you could provide 4 water contents and 4 oxygen offsets and get 4 calculations, but you won't. I know people have asked this before. You won't get 16 calculations, if that makes sense. You won't get every possible combination of them. There is a way to do that. I'll talk about it a little bit later. But yeah, for this, I would maybe like set water at 2, FO2 offset, maybe let's go -1, 0, 1, 2. As we'll see, FMQ -1, FMQ itself, FMQ +1, FMQ +2. These don't actually have to be integers, just to specify. By default, we do often talk about log offsets in terms of, okay, almost integer offset from the buffer. They don't have to be integers in this case. And I'll send that label to FO2 offset. That run. For those of you that are only having it run one model, make sure you're not providing a list for the water contents. Your water needs to be a single value like this. Okay. If you provide this in like this, it will just run one water content. Ludmilla, could you post your what this screen looks like for you in Discord so I can have a quick look? This is what it should end up looking like on here. Excellent, seeing lots of awesome more plots coming through. Okay. So I think Lamilla, because your label is still set on H2O init, it's trying to label things by the water content, but you've only provided one water content. So you need to change your label to be the value that you want to label by. Yeah, I'm just going to go check if that was the issue that Brad had as well, but keep posting if there's any issues. I just had one error pop up. Yes, the error here.
Yeah. Yeah.
So, Brad, what's happening is whether the label is still set each it's trying to label it and it has one big label from. So I think you're basically overwriting.
Did you see at the bottom of your label? This needs to be like that. I was testing something else first. Your label needs to be FO2.
I don't believe so. In terms of using electrons as chemical components, that is not something that is currently possible in melts in this case. So for those of you that only got the one calculation because of the labeling thing, that is really useful to know. It's another thing that I will build in the next version. I will build something in that if you say label is equal to, and it's obviously not the parameter that's influencing the models, it should just return all the models with run 0, run 1, run 2, run 3, etc. rather than labeling. Then at least you get the results. So that's a really useful thing for me to have spotted. That's a potential bug, and it's something that I will work on as we move forward and moving to more discussions. Okay. Yeah, so Jacob, your H2O init is surrounded by the brackets. It needs to just be a single value. As it's a list, even if it's a list of one, yeah, that's kind of overwriting how many calculations Melts is going to do. So you just need to, oh yeah, Alex is already there. Thank you, Alex. All right. So I'm going to give everyone 5 more minutes. I'm going to quickly go grab a drink. We've been going pretty continuously since about 12:30. Yes, yours isn't running, and it never started running either, it looks like. I would try restarting your kernel and running through again. Also, remember to increase the timeout to maybe 180. I said the timeout should have been longer than it is here. That was my mistake. Yeah, I'm just gonna quickly go grab a drink, guys, but have like a 5 minute break and then we'll continue with the rest of the notebook in a little bit. Right, so I'm gonna keep that there on so people can see what how I typed in, make sure that kind of makes sense for them. So the color map are any matplotlib color map. So if you Google matplotlib color maps, any of those will work as color maps for this plotting here. So at CMap, any matplotlib color map in here will work. So you could do uh, reds or reds reverse. I don't actually know many off the top of my head. Uh, Thanks, Sarah. Yep. One thing that is worth keeping an eye on when running this stuff is if it seems to be getting really slow, especially if you've had to restart the kernel every now and then, is just checking you don't have a huge number of like floating Python versions that are still running in the background. And if so, sometimes it can be helpful to come into your task manager or activity monitor. And if there is a Python version running in the background, it's taking up a load of memory or load of CPU usage, just doing a force quit on that process. Um, in that case. And you can see like Zoom in this case taking over a lot. I'm not going to force quit it, don't worry. But that can be something that can be quite helpful in terms of like freeing up some space um, if you notice things are really slowing down. I wouldn't do it immediately, but it's something to keep an eye on. Nice. All right. So a lot of people seem to be getting nice model results. People are clearly also choosing, so Susan, if you make your label FO2 underscore offset, when you run that calculation, rather than being run 0, run 1, run 2, run 3, it will label the calculations by the FO2 offset from the QFN buffer. And I'll show you
Right.
guys.
Yes.
Yeah, so if you have this line in here as that, um, your calculations will be labeled by that FO2. So just to show you guys what this looks like, um, themselves, it will specify it will draw in the FO2 buffer and the FO2 offset itself. I know I should technically have a plus here, a plus there, but I don't, sorry. Um, but yeah, it will draw in the buffer that you have and the offset from that buffer into the label. So this is the label that you will see if you have that kind of label parameter set up correctly in this case. One of the other things that can be quite useful. Okay, Brad, awesome. I did all of them. Okay, thanks. One thing that can be quite useful is if we go into any one of these different options. Let's go into the F2 minus 1 for mine, okay? And we look at what this output structure looks like. It looks very similar to the output structure we had for that single calculation all the way up here, right? Very similar output structure. And it's basically within each individual calculation so in that initial dictionary, there's 4 different items. Each of those items is the result of one calculation. And so this will look very, very similar to what you'd expect to see from that individual calculation if you ran it at FMQ minus 1. Okay. There's one addition though, this input parameter over here on the right-hand side. And this can be quite useful if you're trying to keep track of what you're doing, if you're trying running large numbers of models and you want to really understand how different parameters influence it. If you look into this input parameter, it's actually a dictionary, but it's a dictionary that contains the input starting composition of the system. Okay, so here we have our starting normalized melt composition with 2% water. We know that it tells us which model we're going to run this calculation at. And it tells us other things. It tells us we're doing these fractionating solids, fractionating fluids. We didn't specify temperature of these parameters here. Instead, we specified a step in temperature and an end temperature. And we also specified that we want to find the liquidus. We didn't specify anything in terms of a path in pressure because this is an isobaric crystallization calculation. So we just have a single pressure. And once again, we have our oxygen fugacity information and things such as this. You might note that I have actually suppressed by default a couple of phases down here. This can be turned off. This is because I actually found that in some cases, tridymite was stabilizing instead of quartz or some high silica rhyolites. If you're interested in turning these off, you just have to type suppress equals none into your calculation. And rutile, once again, was popping up and causing some issues in certain places, but can be easily turned. The suppression of rutile can be turned off once again in that case. But yeah, these input parameters, if you're running lots of calculations, this is like really how you can keep track of like what parameters are changing. And especially later on, I'll show you an example where I vary multiple parameters within each calculation. And I'll show you how you can kind of keep track of those parameters in that way. All right. Nice. So it seems like Penny's just shared a nice bit of code of how to make a TAS plot with this using Pyrolite, which yeah, is a nice way of visualizing this data as well. And once again, it shows that you don't really have to do too much coding in order to take these results and plot them up using other tools. All right. Okay, so we have 8 different crystallization models. Well, technically, we've run 9. Some of you guys might have run a bit more if you're waiting around or you decided to add more numbers into there. And we're showing that in terms of the FO2, at least hopefully you guys would agree with me, the high oxygen fugacity crystallization models showed us much greater susceptibility to calc alkaline compositions. We're not seeing a significant enrichment of iron relative to magnesium. Instead, we're seeing this relatively rapid onset of silicon enrichment in the melt phase. Some of you guys showed or shared the Harker diagrams as well, and you don't see a significant increase in the iron content of these 2 lines here, the high FMQ lines here. You won't see a significant increase in the iron content of those melts on the Harker diagram. So the question is, okay, what's causing the difference, right? And this is where using the phase plots once again comes in quite useful. So this phase plot function here is identical in how I've set it up to the one we used above. The difference is that in this case, isobaric crystal H2O has 4 models in it. When we ran it above, we only had 1 model. That doesn't need to change anything. If we run this calculation here, it will run the calculation, sorry, the plotting function, it will run the plotting function, and it will plot the results for all the models that you supply it. Okay. So you can see here in the H2O 0.5, plagioclase is on the liquidus somewhere around 7 weight percent. 2 weight percent water, plagioclase somewhere around 6 weight percent. 4 weight percent water, plagioclase somewhere around 5 weight percent. It's this kind of bluish one in here. And actually it's similar in terms of 6 weight percent system in that case, potentially indicating we're maybe fluid saturators. We're not changing significantly between these different models. Okay, you can see this fluid quite early on in this case. When you do this, when you run this code with multiple models, it should retain the same color for each phase between the different plots. Okay, each plot should have the same color for each phase. So plagioclase should always be this kind of greeny blue in this case. Okay, it makes it easier to compare between them. What I want you to do is use this plot both with the H2O models, so isobaric crystallization H2O, also with the isobaric crystallization FO2 variable you just created. Make these plots, and what I want you to do is kind of compare, let's say, the pyroxene, the plagioclase, and the spinel crystallization onsets, and see if you can work out what is the difference between the models, what's driving the difference in melt chemistry with regards to crystallization histories. And so plot your results in the Discord chat once you have them. What do you think is most important in this case? Is it the onset of spinel crystallization, the onset of plagioclase crystallization? In Melt's world, at least, what's driving that kind of alkaline differentiation trend that we see in those high FA2 or more oxidized crystallization calculations? Nice, seeing a few plots coming in. The other thing you can do if you already got some of the plots working is try changing the x-axis, try changing it by plotting it with temperature. Okay. Or you could also try adding lines equals true and seeing if it's try and work out, do you prefer seeing it with the lines or as the filled stacked plots? What, in your opinion, is the most important way of doing it? Yeah, so Anton said spinel seems quite important, it's quite sensitive to FA2. And yeah, I'll plot up the FA2 results in a little bit and we can discuss that a bit more. But yes, I would agree with you in there. Yeah, so I think a couple of people have been finding, just noticed this on the Discord chat, that uh, these calculations can take up quite a bit of memory. So there's something to be aware of that if we're running relatively long fractional crystallization calculations and you're running multiple calculations at once, they do come with a significant CPU and random access memory kind of cost associated with them. So sometimes you will find that these calculations will either be very slow if you're doing other things on your computer, or doing other things on your computer will be very slow if you're doing these calculations. Um, that is kind of part of the way this works a little bit, in that by doing this parallel processing, we're trying to maximize what your computer can do. But if other things are running on the computer, if you have a load of Google Chrome tabs open, you're running Zoom, you're running Discord, all this kind of stuff, it does all stack on top of itself and can potentially lead to a slight slowdown in the overall performance. So it is, if you're intending to do lots and lots and lots of melts calculations, I would advise to try and kind of like minimize other things on your computer at that point, if that makes
Matt,
sense.
you've shown people how to access the task manager on Mac, but I don't think everyone knows how to access it on Windows. So I'm just gonna kick you off for a
Yes,
second
go
and
for
show
it.
people that.
Yeah.
So on Windows, if you are coming into problems, if you go Control Alt Delete, hopefully you can all see this. Then click Task Manager.
It's not quite loaded yet, Penny, sorry.
Yeah, there we go. Task
Yeah.
Manager loaded now.
Yeah,
Yeah,
it's loaded
okay.
now, yeah.
So Control-Alt-Delete, Task Manager. You then go down here to Performance. Here you
Penny,
can.
Penny, I can only see your ChatGPT.
Oh, okay. Hold on one sec. I'm sharing the wrong screen. 1 second. I was trying to find the best way to. I'm sharing the wrong screen. Okay. Hey, can you all see it now? Let's do this again.
Yeah, just loaded now.
Control-Alt-Delete. Can you see the thing that says Task Manager, Matt?
It's 1 sec, it's being slow.
Oh,
It's
everyone
just
see?
showing a black box.
Okay, maybe it doesn't show the. I'm thinking it doesn't show the
Yeah.
Task Manager thing. Can you all see this now? This is my Task Manager. Matt, can you see this?
Yes.
So he processes, this is all the things that are running. But if you go under performance, you can see these are my different cores and what they were spiking around doing. All I'm doing is running Zoom. So you can see it's already taking 37%. The key thing is the memory here. So here I have 12.9 gigabytes, which is absolutely fine. You will see Lycan post in the chat. She's only got 2.6 gigabytes available. So this is where having a 32 gig RAM laptop over a 16 gig RAM laptop makes a massive difference, because if Zoom and other things are taking up 14 gigs, this means I have 14 gigs-ish spare, whereas they only have 2 gigs spare. So yeah, there are times, like if realistically the thing Matt's going to show you next, where you're going to be running like 5,000 melts crystallizations calculations, that would be the situation where you go find a desktop to do it on that has a bit more RAM. There are going to be points where like your laptop just won't be able to handle it, and at least you can automate it now. But yeah, you'll have to find a computer with 64 gigs of RAM or 32 gigs of RAM, and it will make a big difference to your ability to run these things.
Awesome, thanks. Yeah, if we're going to Task Manager, the Control-Alt-Delete is one way to do it, but also if you just go into the search bar on Windows and type Task Manager, you can get there that way as well, as we couldn't see the other way. Okay. All right, so I've seen a lot of people post their graphs. Can people send a thumbs up in the chat if they've managed to successfully produce the graph of phase proportions? Awesome. Seeing lots of people send through. Perfect. Okay, excellent. Thanks a lot, guys. All right, so I've also noticed in chat that someone, I can't remember who it was, so I've actually lost it now, has decided to skip forward, which is absolutely fine. I love it. And showing the next thing that I was going to talk about. So we have these phase plot. So this is the phase plot for water. We could do the phase plot for FO2 as well. And actually, all I need to change in there is just the variable name, and it will run the plots with FO2. And so you can see in this case, what's going to be really important is this darker blue thinner line in here. The spinel is going to become thicker and is going to move to onset crystallization earlier to actually becoming the liquidus phase for FMQ 2.0. Okay, so that spinel crystallization is becoming more and more important. Now, I find these diagrams really easy to read and visualize. Penny disagrees with me. And so we agreed to make a second plot. And so what we can plot in here is using this PTT phase mass comparison, is this is going to plot for a single phase. You need to specify which phase. Once again, specify the x-axis you want to plot it against. It will specify the mass of that phase between different models. So once again, I can run that there. This will now show me my different water models and show me when the onset of plagioclase crystallization takes place in both models. Okay. So you can see, and the low water model, plagioclase is a near liquidus phase. Higher water content, okay, the temperature. There must, sorry, there seems to be a bug in this code. I will fix that for a future release. It's always plotting against temperature, it seems. In this one, we can't plot against MGO. It has to be temperature. Sorry about that. But in this case, you can see that these other models, there's a bit of a crystallization period from the liquidus until plagioclase starts crystallizing. And for these final ones, there's even bigger crystallization history prior to the onset of plagioclase crystallization in here. Okay. What I want you guys to do is quickly do that for both plagioclase and spinel, for both the water models and the FO2 models. And once again, throw your plots into the chat once you're done.
And also, you can start throwing interpretations in. What does this really mean
Hmm.
for our calc-alkaline versus thermolytic series? What are the key phases that are driving us either way?
And you don't have to do it just with plagioclase or spinel. You can do it with any phase, which is saturating in the models, and you'll be able to see the results. Let's say so, seeing that clinopyroxene is a liquidus phase in the first two low water models, but at lower water contents, it's actually suppressed. It's not the liquidus phase initially in the lower water content models down here. You can also do it with things like liquid and look at how the mass fraction of liquid changes with temperature and differentiation sequence and things like this. You'll notice that these phase names, these are the standard phase names from alpha melts, but there's always a numerical value associated with them. Okay, so we could have spinel 1. In some cases, I don't know if we actually have that here, we might have a spinel 2. Okay, so in the very water-rich models, in this case, we do actually saturate very small amounts of a second spinel phase. So there's some solvus occurring in the spinel field, separating out two different spinel compositions.
Matt, that answers Rose's question actually. Can you just remind people how to look at the phase list quick for each
Yes.
one? Because sometimes what you'll see is that you ran 5 models and you only see 3 lines on your diagram. You might be like, oh, panic. But it's actually likely because either that phase didn't stabilize or Meltz has put it into this spinel 1, spinel 2, or CPX 1, CPX 2. So you can always either look at the mass G or Matt, if you just show the actual phase list as well.
Yep.
So there's a variety of ways you could look at this. You could look at the mass. What I find, honestly, the easiest way is to look at this phase list. And you can do dot unique, Matt, and then you can
Oh,
see.
yeah, good point.
So this is looking at all the unique values. So you can see there you did stabilize a spinel because you have a spinel in that third one. And then Matt,
Mhm.
if you do it for the 6 weight% one, there you can see you've got a spinel and you've got a spinel too. So it can be really helpful to just use this with along with that unique. And Matt, can you just paste that code in the Discord so people have it for their
Yeah,
reference?
sure.
This is what I do, and I'm trying to work out whether Meltz has like taken away my CPX and put it into a CPX too. And perhaps we can get Paula at some point to talk a little bit about, yeah, I mean, Matt, you said it's when it crosses the solvers, but exactly when we get this splitting and maybe how
Hmm.
best to deal with it.
Yeah,
Oh,
go for
hang
it.
on.
Go for it, Paula.
Yeah, no, I was just checking. Um, had the microphone on. Uh, yeah, Paul and I actually were going to come talk about this a little bit tomorrow. But sometimes it's a genuine extra a second CPX because you've got pigeonite. And I don't know if you're going to show that example that I know one of your examples you did use thermobar to show that to plot up pyroxene compositions. So you can see that it's a low calcium CPX. But actually, a lot of times you get spurious extra. Yeah, there you go. So yeah, sometimes it is actually should be there, and but sometimes it's due to parts of the pyroxene. Oh, I should turn the video. Um, Parts of the pyroxene model, like parts of composition space that are not very well calibrated because there aren't any data there. And so you can end up getting extra phases exolved. And if you look at the compositions of them, they're often kind of a little wild. So in alpha melts, we do actually give you the option to limit the number of pyroxenes that you, or any phase in fact.
Yeah.
Okay. Yeah, to limit the number of instances of a phase that you can stabilize, either solid or liquid. But we don't have a good way to limit by composition. So we don't really have a good. We can say maximum two kleiner pyroxenes, but we can't say that we want one of those to be pigeonite and one to be augite. So yeah, but that was something we were going to talk about a bit more tomorrow when Paul is back. So.
And Matt, I'm just quickly gonna so we've come up with this second example that we're not really gonna have time to go into today, but I can just share my screen. You guys can work through it in your own time and obviously reach out for help in the Discord. But what this example does is it takes, Matt, can you see the right screen?
I can see it. Yeah, you're zooming in now, right?
Yep. So you can basically take your mineral chemistry output from melts and put it into these thermobar functions that calculate your ternary points, and then you can really visualize them on this field. So we show you in this example how to do the CPX1, and then the next steps we guide you through working out the CPX2, and then you'll be able to work out, as Paula said, like whether these are actually realistic compositions that we see in magmas or whether like the second CPX is a little bit wonky. And similarly, you could do the same with your two spinels. You could plot them up in on different ternary diagrams. Actually, Sarah, she is working on a Python package which has fabulous iron titanium oxide ternary diagrams. So once she's finished that, you guys will be able to use that to link into melts to help make these as well.
Yeah, some of the kind of like wacky pyroxenes, when you do get these wacky pyroxenes, it's usually just a very small amount. It might not show up on a projection like that, but if you look at something like the titanium or composition, it's going to be like wild. So you might have to go to the actual data as well.
So, Anton, I've seen you just put a message in the chat. Is that using MageMin for the calculations in this notebook, or separately using MageMin? You saw a similar thing.
No, separately. When I use MageMin, especially in the low temperatures, I have two pyroxene and they go like a saw. So you have CPX1, it goes down, and at the same space, CPX2 goes up. If you imagine in your imagination, we'll summarize them, it will be just one proper straight line.
Mm-hmm.
So for some reason,
are they compositionally just like similar, or are they are they flipping the compositions?
They sometimes are very similar. Yeah, but okay, it happens below 800.
Okay, so yeah.
So I'm not sure if it's calibrated for this.
Interesting. Okay,
I don't know much.
Yeah, I definitely know in some cases, like for the MageMin calculations I've done, MageMin will also return multiple phases. Once again, it's a large number of cases it is where there is a true solvus and you are returning multiple versions of the same phase, like a high and a low calcium CPX. But I'm sure there probably are some, especially in the low temperature range where it's probably at the limits of its calibration. Yeah, that might be, it starts to struggle in there. All right.
And we have Paul back now. So, Paul, we were just talking about like why you might get many pyroxenes and how some of them are real and some of them are artifacts.
Yes. So look at the aluminum and titanium contents. The highest ones are likely to be goofy.
Mm-hmm. Yeah, so I think you hear more from these guys on these kind of challenges tomorrow morning, I think is there. Yeah, we'll hear more about the different challenges you face when trying to run melts models and identifying some of these like slightly wacky cases in there. All right, so I've seen loads of people plotting up more sensible things than what I've shown here. But one of the more kind of telling graphs you might be able to produce as a result of these models is these variable FO2 and the spinel proportions crystallizing in. So you see at high FO2, spinel is actually your liquidus phase in here, and this is more of a magnetite than a kind of chrome spinel. And it's crystallizing up to around about 9% of the system becoming spinel by the end of that crystallization trajectory. Compare that to low FO2, where you have That's 50 to 100 degrees of crystallization prior to spinel saturation, and less than 2 grams of spinel saturating within your system. And that can really nicely explain why you're seeing this big change, this enrichment in iron magnesium versus this enrichment in silicon in these two different models in here. So I think most people are seeing a lot of people posting good stuff in the answers tab. Most people like being able to plot similar stuff, and I've seen a lot of people talk about the kind of importance of spinel in that same thing. So for anyone that was able to do the install MageMin calc function without issue, don't worry if you weren't able to do it. I'll just kind of talk through what I'm doing here, and we'll try and get it figured out so everyone can run that at some point soon. I would definitely suggest that everybody who's about to run this increases the timeout. The MageMin calc calculations do take longer. I would increase it. For me, I'm going to increase it to 300. I'd be tempted to increase it to like, even goes like 420, 480, something like that for your timeout if you're going to run this calculation. So if your install MageMin calc function and the test MageMin calc functions worked when you did the install steps, feel free to try running this calculation. You'll notice that I have set this up in terms of the keyword arguments I'm using. I have set this up in exactly the same way as the previous calculation. If I copy that and I paste it up here, it is almost identical in terms of the keyword arguments that we are using when we're running this calculation in MageMin versus the calculation in Melts. Okay. The only difference in here is this model keyword argument. And so once again, we could actually go and have a look. Let me go back down to here quick. We could go and have a look at our help and have a look at the isobaric crystallization help. Okay. And you can see that in PetThermoTools, you basically get a choice of 6 thermodynamic models. You can use p-melts. You can use the original rhyolite melt. So I don't call it rhyolite melts. I call it melts version 1.0.2. And then these 2 updates to the rhyolite melts with CO2 solubility or mixed H2O CO2 solubility, the one designed specifically for granitic minimum, and the one that is recommended for use in other systems. Okay. So you have 4 thermodynamic models that all come under the like broad term of melts that you could use for these fractional crystallization calculations. You then also have these 2 models down here, Green et al. 2025 and Weller et al. 2024. The Green et al. 2025 thermodynamic model is an update of Tim Holland's thermodynamic model from 2018 and has become one of the more widely used thermodynamic models in igneous petrology outside of the MELTS framework. Owen Weller last year, or 2 years ago, I guess now, sorry, released this other thermodynamic model, which is calibrated for dry alkaline igneous systems, but actually seems to return relatively logical results in a wide array of different systems as well, but it doesn't have a H2O term. So calculations done with the Weller model are going to be purely anhydrous. Green does have a water model in the system. It does not have a CO2 model. So once again, if you're doing those saturation pressures, you can't really do these in the MageMin side of things anyway. You have to do it in melts where you have these 2 models that have CO2 solubility built in. Okay. But basically my main point here is if you wanted to switch from running from melts 1.2.0 to the Green 2025, and we're going to use Green because we have quite a lot of water in this ARC system, okay? All you need to change is that model keyword argument, okay? So if you're able to run the MageMin calc installation, you should be able to set this running. And I would expect on my laptop this to take somewhere around a minute, probably. On other people's laptops, it might take a little bit longer. And the reason why this takes longer than melts is not an issue with MageMin. Okay, I want to stress that this is not MageMin being slow. It is the connection from Python to Julia, initializing Julia call, identifying the correct version of Julia, because there's a version requirement in here, and making sure and pre-compiling the necessary packages in that Julia environment prior to the calculation. So I would hazard a guess the calculation hasn't even started yet. That first 40 seconds is just initiating Julia from Python, okay? So it is slower, I'm aware of that. It means running lots and lots of calculations will take more time. But the idea is from one kind of Jupyter notebook, just by changing one keyword argument, you can switch to an alternative thermodynamic model. So yeah, I said a minute and 3 seconds is what that took to run on mine. And I'm gonna let everyone else have a go running that and see if you can produce the 2 plots below. And if you can, once again, post them into the Discord. Let's see if hopefully a few people have managed to get this running and are able to get some results out of it. If you do get some graphs from this, please do send them through if you're having issues. Oh, so Julia got flagged by antivirus. That's always good. And yeah, as Penny said in the Discord, in case anyone missed it, rhyolite melts is not just for rhyolites. Paul mentioned earlier that rhyolite melts is the original melts model with an adjustment to the quartz and sanidine end members. Everything else is the same. So rhyolite melts can be used across compositional space. It has just had a specific tinkering to fit the rhyolitic or granitic minimum at the Bishop Tuff. And really, the reason why doing this here by running these models with MageMin, and we're seeing some results. Awesome. Thank you, Megan and Gustavo. And yeah, feel free to go down and run the second function as well, Gustavo, if you want. One of the reasons for doing this is really kind of want to ask the question, okay, we produce some results. We'll ask you guys what they mean. And a lot of you said, oh, spinel saturating earlier at high oxygen free acid, that's driving the kind of calc-alkaline trend. And a reasonable question to ask is that real or is that Melt's world? Essentially, like Melt's is a very, very useful tool, but it is not perfect. And the question is, do you get the same systematic variation if you were to use an alternative thermodynamic model, an independent thermodynamic model? Would you get the same results? Would you get the same answer in that case? And so, yeah, so a nice comparison by Gustavo here showing the kind of Spinel mass fraction from the MageMin. Oh, that's not, that wasn't Gustavo, my bad. From the Spinel mass fraction in the melts and the MageMin models compared to each other. That's a really nice graph. But then also showing the kind of mass fraction of Spinel in this case. So interestingly, one of your models, Lynn, doesn't seem to have any Spinel at all. Would you be able to check the phase list if you're comfortable doing so and seeing, or the mass data frame and seeing if that is the case? So just to kind of specify what happened there. So one of Lynn's models, and potentially you're running at a higher water content than I am.
I'm going to check. I had changed this from doing the previous FO2 to the MM. I thought that was necessary since it otherwise was just pulling my previous result. And I had only done 3 FO2s.
Oh, okay. Okay, that makes sense. I was just checking there was something that didn't.
Yeah.
Cool. Now I just wanted to make sure this wasn't something that just hadn't run or something like that. That makes sense.
No, I think it just pulled the values I used before, and I had only done 3 for quick testing.
Cool. Okay. Yeah, awesome. I'm seeing a lot of people managing to get results from this, which is excellent. I would say I'm aware there are still challenges installing the MageMin side of this. It's something I'm really keen to kind of like get working properly. And so I really appreciate those of you that have told me that you've had issues installing it, because it's been really helpful. And we've managed to already solve a couple of potential bugs in the installation already this week. Every time someone gives me something went wrong, here's the error code. It helps because I kind of add it to a data set and then I kind of like work out overall what's going wrong. And I can try and improve from there. So yeah, if there are issues, letting me know is really, really useful. So thank you for that. But yeah, and you can kind of, if people are waiting and you've already run this, try setting the FO2 to FMQ+1 and using different water values. Make sure you remember to change the label to be H2O init and then run through the calculations again to see what those look like. This is kind of what I get when I run at 4 different oxygen fugacities. And so this is the FO2 and not the MM, as people were pointing out. And so yes, the FO2 MM, you only get QFM 0.0, 1, and 2, which means, because I did run 4 calculations, if I were to look at FMQ minus 1, and I was to look at the phase list dot unique, the same code we looked at earlier, yeah, at this very low oxygen fugacity in here, there is an ilmenite being formed, but there is not a spinel phase. Okay, so similarly to how melt, so alpha melt separates out those spinels and rhombohedral oxides, MageMin is doing the same essentially here. So we have spinel, and spinel is including magnetite in that case, but is not including ilmenite here. So we could potentially look, see if ilmenite is important in others, and unsurprisingly, yeah, it definitely is. One thing that I've not actually looked at in detail to test extensively is MageMin will return an amphibole phase. I don't know if anyone's actually gone and compared the compositions predicted in this amphibole to natural amphibole systems to see how reliable or accurate it is. It'll be a very interesting project. Oh, there we go. Anton apparently has compared. Sometimes makes sense. Okay. That sums up thermodynamic modeling, I think. Yes, we did.
If you want, I can just quickly share my screen and talk through what we did in that paper.
Yeah, go for it.
So when Matt was first putting together PetThermoTools, one of the reasons was we were writing this review chapter of PTX conditions of magma storage. I've pasted a very low res PDF. If you want a higher res, please request it off ResearchGate. This has the worst paywall I've ever seen of any articles. What this is basically doing is we took fractional crystallization experiments from this anhydrous tholeiitic basalt. So that is these blue squares here. And then we ran at the experimental pressure using P melts, which is shown in cyan, using rhyolite melts 1.0.2, using rhyolite melts 1.2.0, so that's the blue and the green lines, and then using MageMin in black. And you can see, for example, for calcium, MgO, they all show very similar, but actually if you run in Petrolog, you get a completely wacky result. You can see in general, none of them did a good job of the silica magnesium systematics. And similarly, we ran another one for these are wet fractional crystallization experiments from Nandikar. And again, what this is now showing is each model is shown as a different panel and then showing 4 different pressures on there. So again, you can kind of visualize the difference between the different melts and the MageMin versions. But generally, if you're running fractional crystallization, now you have access to this MageMin. It takes a bit of time, but I would say it's always worth, if you're coming up with like a hypothesis about your magmatic system purely based on melts 1.2.0, it's always good to check that that same thing would be true in MageMin, because if it's not, that's the point in which you'd want to ask yourself by, say, looking at experiments, okay, which one of these models is actually doing a better job of these phases, because you don't really want 2 different answers just based on the model that you choose. So at that point, yeah, we do some more comparisons, and we're going to show an example of that tomorrow with the phase diagram code that we're going to use for Manolera as well.
Yeah. Awesome. So yeah, it seems like loads of people have been getting this stuff run, which is awesome, because I was worried that no one would be able to install this. So it's great to see that it seems like the majority of people have been able to install the MageMin calc. Okay, I realize that it is quite a bit slower. So if it's still running, I'll just give it a bit more time, increase that timeout, that kind of thing. And yeah, you should be able to get these graphs. So I think it's quite convincingly showing that regardless of which thermodynamic model you use, increasing the oxygen fugacity, as you would expect, increases that kind of oxide stability, pushes the system towards these calc-alkaline trends far more than you would otherwise expect. And so what we can do, just to kind of like double check that, is we could take this Harker plot, and the Harker plot is going to work just as well with the MageMin calculations as it will with the melts calculations. The outputs are exactly the same in their structure. And so all we need to do is replace the vial in there, and this Harker plot should now plot, yeah, nicely these kind of MageMin calculations in this case. And you can see in here, oh God, that the high FO2 calculation shows this initial little kick up in iron, but then
compared to all the other systems, it drops down rapidly and shows this iron depletion trend, as you'd expect from that kind of calc-alkaline systematics. I appreciate that it's not producing a brilliant fit to any of the data in here, apart from some of the medium oxygen fugacity ones, maybe fitting some of the OCMOP data relatively well, but it hopefully shows a difference in kind of the trends and how oxygen fugacity might be able to influence it. Okay.
Matt, what I would maybe suggest we do now is we've used these custom plots quite a lot, but maybe we should get people to just make a very simple silica versus MgO plot and plot one mage min and one melts run onto that, just so that you folks can practice accessing these data frames within this stacked nested structure. So yeah, basically choose one water content from your melts run and one FO2, and then choose one from your mage min. Hopefully they'd be similar, but not the end of the world if you haven't got that overlap in your runs. And just plot, maybe let's do actually iron versus silica, just so you can practice not using these custom plots, but making your own plots.
Yeah. Yeah, so be a good, that's right. It's a good way of like making sure you understand how to export, get the data out from these output structures, essentially. So you have these kind of like nested structures in here. So you have that overall dictionary that contains each of the individual models. You can then access any of those individual models. Let's see if I can just copy this in from here.
And remember, anytime you don't know what the things are called, use that .keys function.
Yeah.
And then I would just advise you just copy it straight, because you're going to make so many typing errors otherwise.
I mean,
I rarely type anything when and Matt does, but I rarely type anything when I code. I use.
Okay.
So yeah, we'll give people a few minutes to have a go at that, just to check they really understand how to access this.
The one thing with the MageMain calculations is they are quite memory intensive. So they do tend to take up quite a lot of your memory. So this is where it's very important to make sure that yeah, things are minimized in terms of other processes happening on the computer. So it might be worth sometimes just like checking this, seeing if this runs after we've finished up on the call here. Yeah, there doesn't seem to be any issue, obviously, in that, Anton. It's possible it hit a timeout. It shouldn't have returned that error if it hit a timeout, though. Yeah, I mean, try increasing it to 600 and just seeing if that works. I know that's kind of annoying to wait 10 minutes for it. But yeah, I'm a bit confused by that error, because if a calculation is run, it should have the mass G column in there.
A question, if you come back to the notebook in a few days. Yeah, that's a good question. So the what Brad's asking is basically, now you've run this thing, will these data frames stick around? They will stick around in Python as long as your like environment, like you don't close it, but you can always save these to Excel super easily. So Matt, do you want to show the ways to save these outputs to Excel, or should I take over? Are you helping someone else?
Feel free to take over, because I don't have that right on the top of my head.
Okay, yeah, let me share my screen super quickly. Hopefully, can you all see? I just need to zoom in a wee bit. Oh, where's it gone? Oh, hold on, let me share the other screen. Why is Zoom so difficult? Sorry, folks. Let me just share this screen. Can you all see my Python thing, Matt?
Yes.
Okay, so what you do is you would literally take the name of your art, because this is a dictionary, we're going to have to write it to a pickle. Okay, give me 2 seconds to pull up my so a pickle is 1 second. A pickle is a Python funny way of like preserving something for later. So in the same way you like pickle a gherkin, you pickle a piece of data. So what you're going to do is we are going to import this package pickle. And then we're basically going to open up this thing and we're going to dump it. So basically this is just the name of the variable here. And then you can load it back in later. I'm just copying these from my Python notes. So you can load it back in later from these 2 bits of code. I'll paste these in the chat. We can just call this test pickle so that you can see that it actually works. So first we dump the pickle and then we open the pickle. You can open this in any, like a new notebook. So you see this test pickle thing I've dumped, I've loaded, sorry, is exactly the same as this thing I've so you can see that they're exactly the same. In terms of what that looks like in my file browser, let me just pull it up. One's from GitHub. Sorry, 1 second, folks. Where's the pickle? Here we go. Okay, so you can see it is now here as this PKL file. So in general, yeah, and these aren't very big either. This is like 858 kilobytes. So it's a very efficient way of saving data. So I'll just paste this in so you will have it. So this is what you would need to do if you're dealing with a dictionary. So you can all give that a try. You can also save an individual data frame, which is much easier, and I don't have to reference my notes for, but I'd forgot that that's not what we're doing. So if we were to just want to save like a set data frame, so say you were to want to output the FO2 is -1, and then you would want to output, say, all. So all is basically all of those data frames combined. So that would be the data frame you're saving. You could just call this, you can actually just do to Excel, and then you give it a name like test output XLS. And then that will save that to Excel. And I can go into, I'll paste this into the Discord as well, so you've all got it. If I then open up here, test output, we can see that this would be a great thing to put in a supplement, for example. So you would say this is like your liquid run FO2 with this pressure, and it's got like all of the columns that someone would need to recreate your study. There are also ways in Python. Matt, there's a horrible reflection. Can you turn off your mute for a second?
Yes, sorry, 1 second.
Sorry, I've lost you all now. There's also a way you can like output multiple different parts of a data frame into a single Excel spreadsheet. Again, this is the kind of thing that ChatGPT is honestly amazing for, so don't worry about like memorizing these tricks anymore. I bothered to memorize them before ChatGPT came into being. But you could just say like, I have this dictionary and it's got all of these keys and I want them all in one spreadsheet with different sheet names, and it will just like do that perfectly. So that is an option as well. Cool. Anyway, sorry for interrupting, Matt. I just wanted to show Brad how to do that. So yeah, basically run melts once. How I run melts when I'm publishing papers is I'll have one notebook that's like the calculations. They'll save to a pickle, and then I'll have a second notebook that loads in those pickles and just makes my plot. So then I only ever have to run these melts calculations once, if that makes sense to everyone. What other questions do we have? Okay. Cool. Matt, did you want to show something else? You're muted. Matt, you're
yes, yeah. Sorry. There is a way, and I'm going to post an example of this on Read the Doc shortly, of basically because the output structure for these calculations is a dictionary with multiple data frames in them. There is a way that basically will save, and Penny may have already spoken about this a little bit, save each data frame into a different sheet of an Excel file. So you have an Excel file per calculation, each sheet representing a different data frame from that calculation. the one complication is one of the outputs currently, the input variable is a dictionary, and that variable doesn't progress into an Excel sheet very well. So you can do it, you can export everything to Excel and have a method to do this for everything other than the input variable. I'm just trying to adjust it at the moment so you can get the input exported with that material as well into Excel. And then you can just save your output as an Excel sheet and load that in at a later date if you want. So I'm working on an example to do this hopefully efficiently. And once I have it, I will post an example and read the docs of how to move things into Excel, and the vice versa. If you come back another day and you want to load your run back into Python, load it back in from Excel, and you'll have the same structure that you can then use and go on and plot things. So yeah, that is a very good question, Brad, and we'll hopefully soon have a much more efficient way of doing it with examples and read the docs. You're muted, Penny.
Amateur hour over here with Zoom. So we asked you all to make a plot. I'm curious how people got on. If you haven't managed to do it, that's absolutely fine. We can talk you through how to do it. So this is my plot. This is showing the FeO versus SiO2 for both Magemin and melts at 4% H2O and QFM. So this is what we're looking for. I know we've been talking about other things, so we're just going to give you a few more minutes of silence to work on these plots. If you have no idea how to start, hop into a breakout room with me and I can talk you through it if you're like totally like, I don't know what to do. And then we'll go through it with everyone a bit faster. I'm going to hop into breakout room. What am I doing? Breakout room 3, I will join. And then you can all join me there.
Okay, yeah, so whilst Penny's doing that, for everyone that's still here, I'll show you basically what I am working on, which is this. I've copied it into here from another notebook. And this code here basically is going to take this input variable, or the results variable that we had here, and it's going to save it as geology output 2026, because and then we can see, hopefully if I can work out where I put that file in my file structure, should be in here. Okay, so that has now just opened, but we'll work out where it is. Okay, yeah, so that output, that section of code is now going to produce this output here. So you can see all the different parameters that we had in the system, including like the composition of the olivine, the properties of the feldspar, the composition of the feldspar. All of these different materials and compositions are going to be each individual sheet. And so the one thing that is currently missing in here is there is no input data frame, but you can still see like the mass of each phase that can be exported from the system. You can see your phase list at each indice that will be kind of listed here, the kind of like shorthand for each phase listed in here. So this is, I'll share this via Discord, but this is the basic code that I've been using to export each data frame from the results into Excel file. As you could do this, you could loop through all the different files in your thing and create an Excel file for them. I'll copy that into Discord in case anyone wants to use it. And then you can save your calculations and the invalid characters pattern. This is for the things like I have the underscores and backslashes for indicating like kilograms over meters cubed for density and things like this. And so that will save your results into Excel, and you can load those Excel sheets back in and use them moving forward. So see if I can do that now. I believe to do that, all you would need to do is just read Excel. We can just actually call this file path, and sheet name equals none here. We'll load in all, and all now is the original dictionary. So all here is identical to this output that we saved. So this block of code here is how you would save it to Excel. Then once you have it in Excel, you just need to load it in. And the key difference is if you say sheet name equals none, it will load in every sheet from that Excel file, and it will give them the name of the sheet in Excel. Okay. So this is how you kind of load back in your data into PetThermoTools, into Python, and it will have exactly the same form so you can use it again. So yeah, these two cells here for saving your files as Excel sheets or reloading them in. Pull the legend labels from both HTO and FO2 simultaneously for this plot. One way you could do this, I think, Lynn, one thing you could try, let's see if this would work. Combined results. And then you could try and do yeah, so basically in this combine you can make a new dictionary. You can then update it and this will append the two separate dictionaries into one thing. And then each item in that dictionary will have the key from the original runs that you ran. And in that case, the labels will come with them. So when you plot them up, it will show all the keys there. Obviously, this is a bit of a whether or not you actually want to do this, because the problem is it doesn't label, for example, it's H2O equals 2, FO2 equals FMQ minus 1. If you wanted to include that label, so you wanted to include H2O and FO2 of that parameter in the label, you would have to relabel it based on the input parameters that are saved in the input dictionary. If that makes sense. So not sure if I answered your question there, Lynn, but
yeah, you did at the last part there. I was wondering if it made sense to add it from the on the rock camera. Add it from the input dictionary.
Yes, exactly. Yeah. So you could do that. Yeah.
Format. Okay, makes sense.
So for any of these, for like the isobaric FA2 -1, you could put inputs, and then here you want the comp. I know it's a lot of like steps to get there. Whoops, I shouldn't have run that one. And there'll be two. So like you could
pull that out as a format.
Exactly. There are ways to kind of pull that out and add it into the labels. Yeah. It's a little bit clunky, I would admit, but you can do it. Cool. All right. So has anyone else managed to get a plot going? Nice, Alex. That's good. So Alex, did you add the H2O liquid? Did you just add that as a little text box? Oh. Oh, yes, you just annotate. Nice. Yeah. Yeah, so there's a nice comparison of water at 2, I'm guessing, for the same option for Yasti as well. And so yeah, there are other ways to label these plots. And Alex just showed a nice example of that. He like helpfully plotted in his code as well of how he did it. All right. Okay, so Brad, what I think's happened there is that either it's timed out or um or you had run into a memory issue and the system and the Julia system crashed, in which case it will wait for the timeout and then go to none. That isn't something I've come across often, usually when running far more calculations, but it's possible with Zoom and other stuff running that might be the case. Um, I would expect the CPU usage to go to around 80%. The fact it hasn't dropped down is concerning to me. What I would do is check your task manager and see if there's any zombie processes, essentially. See if there's a process that never exited properly. And that might be something if you do find like a Python process that's running in the background, you might want to force quit.
Okay. Yeah. Yeah,
Because
it's
yeah,
strange. It's at 80% whether I'm running this cell or not. So it's funny that it's not changing at all when I'm running the cell. But it
yeah. So
was
usually like if I had something like that where like my CPU's just not dropping, I do sometimes just come into activity monitor or task manager, depending on what I'm using, and basically scroll through and you can actually see I've got a whole number of Python processes that in here. These are not using CPU, but if you have any that are like using up CPU, you can like taking it up, you can just like force quit on them essentially. So for
got it.
anyone using uh, Mac, just that for Windows, it shouldn't it shouldn't leave these number of hanging processes. This is probably because I've been restarting the kernel during calculations a number of times. And in this case, it's not having like a penalty in terms of the CPU usage, but sometimes, especially not often, but I have occasionally had an issue where things haven't ever terminated properly. And once again,
Okay.
something I'm
And
trying to improve on, but yeah.
same with memory. I think I might have typed CPU, but it was memory actually that was at 80% that whole time.
Oh, okay. I mean, memory at 80%, depending on how much memory you have in your computer, isn't as much an issue.
Yeah.
Um, but yeah, it still I would expect it to increase more when you're running the calculations. So yeah, I would encourage you to try and make sure that like background processes are at a minimum. Make sure there's no floating zombie processes that never terminated properly, and then see if it runs a bit better.
And the best way to find out about those floating zombie processes are in the task manager. There's no way to say end all the other things on this.
I think if you completely close down Jupyter and like
Oh, okay.
that will probably get rid of them as well.
Got it.
But I generally find it easier just to go into Task Manager. And if you order by like CPU usage, you're looking for something that's using like inordinate amounts of CPU given the fact it's not returning anything, basically.
Excellent. Thank you.
That's right. All right, so we have a few minutes left. So I'm going to talk about um, okay, can I get the saving to Excel item to work? Um, I'll come back to that in a second, Rose. And
Get them to share screens because I think saving outputs is going to be really, really important for people. So let's debug it for everyone.
so, yeah, sure.
I think it's going to be worthwhile.
So, yeah, Rose, if you want to share your screen, we can potentially work out what's going on. Because I think what might be happening here is, yeah, so I think your FMQ -1 maybe didn't run to completion. And because you only have 3 lines being shown there. So if you scroll up to where you ran the calculation, yes, although it says completed 100%, if you make a new cell and then do isobaric crystal FO2 mm.keys. So if you type in the name of that variable .keys, Yeah, so I think what's happened here is that the timeout of 90 seconds was a bit too short. I would increase that to maybe 180, give things a chance to run to completion. What it probably means is that Magement is struggling with that low oxygen fugacity run. It's struggling to find equilibrium, calculations are taking longer, and as a result, it didn't get to the end of the calculation before the timeout call. And so yeah, if you're not getting all the outputs you want, you kind of need to check in, do I think you is it worth increasing the timeout, or is it that calculation is just not going to work? And it sometimes can be very hard to distinguish between the two in that
Okay,
sense.
thank you.
Cool. So hopefully that runs. Let us know if that works.
Thanks.
And yeah, perfect. Awesome. So I know we told people until 3, so I'm going to quickly show one more thing, and then we'll stay on for a little bit to help people kind of sort out last few issues and things like that. But this is something that I don't advise people to run in the workshop, especially because things seem to be very slow with Zoom. But basically what I've done here, so this is something that, say we wanted to really do this properly rather than just running 8 different calculations. We wanted to run hundreds to thousands of calculations to assess how these parameters influence calc-alkaline versus photolytic trends. What I've done here is several things. So this first line is taking all the compositions between 7 and 10 weight percent magnesium. So these are these kind of Boolean true-false statements that Penny kind of outlined earlier. I'm going to remove the volcano column because I only actually want just numerical data in here. And I'm going to create a covariance matrix. Okay. Within that covariance matrix, I'm then going to sample from that covariance matrix. Okay. So I'm basically starting with, I think it's somewhere around 10 different samples. I'm going to randomly sample from that, assuming that assuming the relationship between parameters is defined by the initial covariance matrix, defined by the initial compositions. Okay, so I'm randomly sampling within the compositional space defined by the true data. Okay, so I'm actually generating in this cell here, I'm generating 500 compositions. I'm checking that nothing has a composition less than 0. So this is once again making sure we keep some small amount of those minor components present within our system. That actually is greater than or equal to 0 in here. It's very unlikely to land on 0 itself. And so I'm generating 500 hypothetical starting compositions for the elutions. Okay. And I'm going to add those to a new data set in here. So this is showing magnesium against silica. The blue is our initial data, and the yellow is the kind of resampled hypothetical starting compositions for crystallization calculations in the elutions. Okay. I am then going to create variables for water, for FO2, and for pressure, all of these that are the same length as the resampled data frame. So they should be 500 long. Water is going to be between 0.2 and 8 weight percent. Oxygen fugacity between -1 and +3, and pressure between 500 and 5,000 bars. So this is random random between 0 and 1 times by 4,500. So from 0 to 4,500 essentially, plus 500. So overall, this parameter will give a random number between 500 and 5,000. Okay. I can then load the new resampled starting compositions, the pressure, the water, and the FO2 buffer parameters I've just defined here into the isobaric crystallization model. The important thing being all of these parameters are the same length. Okay. When I wasn't using Zoom, this took around 5 minutes on my computer to run 500 fractional crystallization calculations. 4 of them did not work. 4 of them crashed and did not return results. Maybe that's my timeout was too short. Maybe I could increase that and test it again. But in this case, based on the fact of CPU usage dropping significantly, I think that was actually true crashes in the calculations. So I got less than 1% failures from 500 calculations. And you can then plot them on the same way we were plotting before. So this is almost identical code. And here. And the only difference is what I'm showing here is everything in red is when the oxygen fugacity is more than 1 log unit above FMQ. Everything in gray is when it's 1 log unit or less above FMQ. So it could be negative or up to +1. And so this is kind of like, if you were to really try and do this, you could generate 500 crystallization models and really start to investigate those parameters. You could use the input parameters that are saved to build up correlation matrices, to look at like how the photolytic index, so the iron content at 4 weight% magnesium relative to 8 weight% magnesium, how these parameters are influenced by those initial starting parameters, the FO2, the initial silica content, the water content, the pressure of the system, and things like this. You may be thinking that this would take hours and hours to run on your computer. That might be the case. The thing with PetThermoTools is as long as the timeout is set to long enough, it will run. It should run all these calculations. It shouldn't hit a failure where just
Will you
nothing
not
is
eventually
returned.
run out of RAM, Matt? Is that strictly true? On a very
RAM is more of an issue for the measurement calculations. And also the way the sub-processes work, the RAM is reduced every time a process finishes. So there's argument, so it shouldn't be the case, but obviously I can't guarantee that, and we have had some issues with RAM, especially with the measurement calculations.
keep your taskmaster up, and the way you can do it, so again, Matt has a very fancy laptop, I have a very unfancy laptop. The way I tend to do this is split the calculations into bits, save them into pickles, and then load all the pickles in at once. So rather than trying to run like 5 phase diagrams or 1,000 calculations at once, I'll run all the ones at FO2 is 0, save it as a pickle, and then restart, run them all at once. So even if you have a rubbish computer like I do, you will be able to save things as pickles and then load them again later.
Even on my computer, I probably wouldn't go beyond like the 500 calculations I've done here. I have a high-powered desktop in my office, in which I've done like a few thousand calculations within an hour with no problem. But it does get into the point where you're doing this kind of number. It does unfortunately get to the point where what you're running it on really matters, and like it exponentially increases how long it will take. But this is possible. This is possible in PetThermoTools. It's kind of the kind of idea of what I just wanted to kind of briefly chat about there.
I think we should maybe get Brad. Brad, you obviously inspired a lot of this with your AGU talk you gave. Do you want to explain how you had to do this?
Yeah, this is I feel both in awe and very excited for this, but also just a tremendous feeling of like, God, I wasted a lot of my life doing this.
Sorry,
So
Brad.
for everyone's no, this is wonderful. For everyone who is not familiar, I did 11,000 different runs with 8 different starting compositions at a wide range of water contents, a wide range of FO2, a wide range of pressure, and then and it took over 4 months to run all of those on Excel melts. So I literally like I would come in the morning and Excel melts would have failed on one of them and then it would just completely fail and then I would have to copy and paste what didn't fail and start again, and that was 4 months. And then in addition, I now had 11,000 Excel spreadsheets with, 15 different sheets. And now we are defining those as the dictionaries. And so I have to then load that all into MATLAB, and then I did some MATLAB stuff. So this is tremendous. It's amazing that and so essentially Matt was just saying that he was able to do that entire parameter space in 5 minutes. And yeah, that was, using Excel melts could have taken months and months. So very exciting. Oh, frustrating that that's how it was back in the day, but hooray for progress.
But it's taken 3 years to get to this
Yeah, it
stage,
took
so
a long
that's slow
time.
as well.
Yeah, okay, good. Yeah. I'm very
Okay,
excited. Thank you.
Matt, should we just summarize what we're up to tomorrow then?
Yes, I'm just going to quickly point people towards in the GitHub data frame. I know Penny already pointed out the activity 2 part 2. If you want to run more crystallization models, see how it interacts with things like PySolveSat, please do check that out. We're not planning on going through it tomorrow, so that is a separate thing which we encourage you guys to look at if you have time.